Okay. So we're going to start talking about second derivatives today. I should finish this up tomorrow. Wednesday is advising day. As of now, I do not have class planned, so there will be no class on Wednesday. If anything, I'll just post a little video for everybody to watch on Wednesday before you come to class on Thursday. I also will be out of town this Friday for a conference, so there won't officially be class either. So we're not meeting for class Wednesday or Friday. But like I said, I might get some video posted, just like a 30-minute video for everybody to watch. So I will let you know tomorrow if there should be a video for you to watch on Wednesday, and I'll let you know on Thursday if there's a video to watch for Friday and over the weekend. Okay, but again, overall, I was pretty pleased with the exam, and I think people generally did well. So I was happy when everybody helped and made it really easy to grade. Okay, everybody have one of these second derivatives and graphs handouts? Okay, so what we talked about in section 4.1 was basically how do you tell where functions are increasing or decreasing. You can also using the critical numbers, and if the derivative changes sign at a critical number, that's how you can get your local maxes and local mins. In the next section, after we talk about second derivatives and graphs, we'll be doing optimization problems, so finding where functions have absolute maximums or minimums. Abel, I have your exam, so just let me know before you leave, and I'll get you a copy of that. Okay. So we took care of knowing when a graph is going up and when it's going down using the first derivative. Whenever the first derivative is positive on an interval, the graph would be rising on that interval. Wherever the first derivative is negative, the graph would be falling on that interval. And then, like I said, furthermore, if you can find the critical numbers and the derivative changes signs at a critical number, that tells you where your local max and mins are and what those values are. Okay, so we're going to start talking about 4.2, second derivatives in graphs. We'll talk a little bit about what the second derivative is doing for us. First, I will define concavity. Okay, so the graph of a function f is concave upward. And we'll talk about why this ought to be the case on the interval AB if f prime of x is increasing. Okay. I.e., I'll write this down. You might want to add this note. That's you're increasing whenever the derivative is positive.
Hello?
Yeah. Oh, you need one of these too, don't you? Well, in that case, I might as well bring you your test. So your concave upward on an interval AB, sorry, I should say second derivative is positive. Okay, so wherever the first derivative is increasing, and we know a function is increasing if its derivative is positive. So we're going to see this notation, but if your original function is f prime of x and that is increasing, that means its derivative, the second derivative, should be positive. Okay, so a function is increasing, that means that its derivative is positive, so that's going to be our definition for concave upward. And then I'm going to be lazy. The graph of a function f, well, I'll just write the whole thing down. I won't be lazy today. The graph of f is concave downward on a, so on an interval, if f prime of x is decreasing, okay, and if a derivative is decreasing, that means its derivative, so the second derivative would be less than 0. Okay. And let's see, do I have a couple shapes down here? So first, let's talk about the notation of a second derivative. Okay, so again, our definition for concave upward, if the derivative is increasing, meaning slopes of tangent lines are getting larger, then the graph would be concave upward. It's concave downward if the derivative is decreasing, meaning slopes of tangent lines are becoming smaller and smaller. Okay, and then since I have introduced this double prime notation, that's notation for a second derivative. So after you take the first derivative, you can take its derivative to find the second derivative. So notation. Okay, so for a function y equals f of x defined explicitly, the second derivative of f, provided it exists, is, and we're going to use just a second prime. So right, the first derivative has 1 prime tick mark, the second derivative has 2 prime. F double prime is going to be defined as the derivative with respect to x of the first derivative. Okay. Another notation, and this is where this might come from, so this is one way to write it. But since f prime of x is also written as dy dx, right? If y is f of x, you can write f prime of x as dy dx. Another notation you can use, we're not going to use it very much though, is this d2y over d2x, or d2y over dx squared. So you think about it this way, the derivative with respect to x of the derivative dy dx, you're just multiplying the d's to get a d squared. Dx times dx is dx squared. Okay. Like I said, I won't use this notation very often. I'll just stick with the double prime notation. Just remember that that's just notation for the derivative of the derivative. Okay. All right. So a couple examples. There's different possibilities for being concave upward and concave downward. So graphs that are concave upward, they can still be either increasing or decreasing functions. Okay, so let me just turn this a little bit while I write on the board over here. So they have this little table for the second derivative and the sign. So if the second derivative is positive, that means the first derivative is increasing. Okay, that means the graph of f is concave up. And a couple shapes that you could have could be, I guess, looking basically like a parabola, right? That's opening upward. Maybe you're strictly decreasing, or maybe you're strictly increasing. So those would all be cases of a concave up shape. And man, I don't know why, but it is hot in here. I think it's probably one of the hottest days we've had this year. And like I said, I think the building schedule and the heating schedule is behind for whatever reason, so it always takes a few days to catch up. Okay, and then if the second derivative is negative, that means the first derivative is actually decreasing. If the first derivative is decreasing, you're concave down. And common shapes are, on that piece of the graph, you might just be opening downward like this. Maybe there's just a single increasing part. Actually, I guess this would be increasing. Or maybe you've got a decreasing piece. Okay, so those would all be shapes of something that's concave down. Now think about what's happening on the graph. So just in this one case, so say your graph is concave upward. Okay, think about what's happening to slopes of tangent lines as you're moving from left to right. Right, so over here maybe your slope of your tangent line is negative, but as you start getting closer to this low point, right, the slopes of these tangent lines are starting to increase, becoming more and more positive all the time. Okay, so when you're concave up, that's how I know the first derivative is increasing, because the slopes of the tangent lines are increasing as you move across the graph. And the same thing would be true in the opposite direction. If something is concave down, you look at slopes of tangent lines, but they're always this time decreasing, right? You start out with a positive tangent line, and then they get smaller and smaller positive values. Up here you'll have a slope of the tangent line being 0, and then they become negative and more negative. Okay, so when you're opening downward, the derivative is decreasing. When your graph is opening upward, the derivative is increasing. Okay. So essentially you're saying the rate of change is increasing or the rate of change is decreasing. Okay. All right. So with this now, we should be able to put together some pretty nice sketches of graphs. Okay, we'll be able to get a pretty good shape. You take the first derivative and use the first derivative test to find intervals of increase, decrease, and local max and mins. And you can take the second derivative, and that'll tell you whether something is curving upward, i.e. concave up, or if it's curving downward, concave down. And then Abel, I don't know if I announced it before you got here, but there's no class on Wednesday or Friday. I might be posting some videos for everyone to watch, so I'll let everybody know tomorrow if there's a video Wednesday, and I'll let you know Thursday if there's a video Friday. Okay. All right, so example 1, we're going to take a pretty basic function just when we do this first. So, and what I need to do is turn this back over here. Okay. So example 1, we're going to look at f of x equals x cubed. In fact, let me stick with blue or black because green for some reason has a bad glare on the videos. Okay, so we're just going to take the basic cubic function f of x equals x cubed. We'll determine on which intervals the graph is concave up and the intervals on which you're concave down, and then we'll just sketch a graph by hand. Okay, so one thing we can do is take a derivative, f prime of x, which is going to be 3x squared. Okay. Notice this is always positive except for at 0 where the derivative would be 0. Okay. So there's a horizontal tangent line at the origin by what we talked about last time. You can take a second derivative, which is just the derivative of the first derivative, and you should get 6x. Okay. Now, just like for the first derivative to determine intervals of increase, decrease, you find the partition numbers of the second derivative. So where is the second derivative 0 or undefined? Okay, so f double prime of x, which is 6x, this equals 0 or is undefined at what x value? Okay, so I think it's only going to happen at 0, right? Because 6x is a polynomial, it's defined everywhere. So the only partition number is going to be at x equals 0. Okay, so that's the only place the second derivative is 0 or undefined. So now you make a sign chart. Now, when you make a sign chart, make a inequality number line, make sure you're labeling that this is the sign chart for the second derivative, right? I could have done the same thing for the first derivative. I could have done that sign chart. As a matter of fact, let's just do that anyways. So let's say I was using the first derivative test for intervals of increase and decrease. The first derivative is also 0 or undefined only at 0. So you can put down 0, but the first derivative is going to be positive to the right or to the left. So this function is always increasing except at the origin 0. Okay. And then you could do a sign chart for the second derivative. The only the only partition number of that would be at 0. Okay. And what's the sign going to be on the second derivative if you're to the left of 0, i.e. what happens if you plug negative numbers into the second derivative? Okay, you're going to have negative, so you're always negative to the left of 0. And then when you plug positive numbers into the second derivative, you're going to get a positive value. So the second derivative is always positive over here. And then what I like to do is you can just do this. Over here, to the left of 0, we're going to be concave down because you got negative second derivatives. To the right of 0, you're going to be concave up. So a review from last time, are there any local max or mins with this x cubed function? There's only one critical number, but what happens to the sign of the derivative as you pass through it? Staying the same, so there's no local max or mins. And then we'll talk about what happens at a partition number for the second derivative. If your second derivative changes signs, we actually call that an inflection point, but I'll define that in the next example. Okay, so the concavity changes at 0. And now if you're going to draw a graph of x cubed, one point we know on the graph would be the origin. When I plug 0 into the function, the output would be 0. Okay, now what happens to the left of 0? So first of all, the first derivative is positive, so it's increasing. But the second derivative is negative, so it's concave down. So I think we're going to be looking at that shape to the left of 0, right? That's the increasing concave down case. So you'll be up like that until you get to the origin. And then from there on, first derivative is increasing. Second derivative tells you you're concave up. So I think we're in this condition right here, right? That's the increasing concave up case. So now to the right of 0, it looks something like that. There's a good rough sketch of the graph of f of x equals x cubed. Okay. Like I said, you can compare the graph. The function's increasing but concave down because of what happens to the left of 0 with the first and second derivative. To the right of 0, you're still increasing but you're concave up. So you have a more curling upward shape. All right, any questions for that first example? I did an extra step of doing the first derivative test to tell me where it's increasing and decreasing, whether it's local max or mins. But it's always increasing, so there are no local max and mins. And that's also confirmed with the graph, right? There's no little peaks and valleys in the inner part of the graph. All right, so everyone okay so far? That was just a little brief introduction into that. Okay, so now inflection points. So I think I said earlier, so for example, in this case, any number where the second derivative changes in sign, either from positive to negative, is what we're going to call an inflection point. It's also a place on the graph where your concavity changes. So right, if you look at the origin right here, you were concave down to the left, but then changed to concave up to the right. So 0 is what we call an inflection point. And it has to be a point on the graph. Okay? So in this case, this 0 is in the domain of the original function. It's not always going to be the case. You might have a vertical asymptote where the concavity changes. In that case, that would not be an inflection point. Okay, so it's kind of like the critical number, right? You only get a local max or min if you have a partition number in the domain. And you only have an inflection point if the concavity changes at a point in the domain. Okay. Oops. Let me make sure this is still doing its thing. Okay. All right, so actually definition first. And then for the people watching the video, in case you don't have your handout, I'll write it down. An inflection point is a point on the graph of a function f where the concavity changes. Okay. And then in symbol form, right, it's a point on the graph where f double prime of x changes sign. So wherever the second derivative changes sign at a number in the domain, that's what we call the inflection point. And I think I've got kind of all four cases down in theorem 1 on the handout. Right? So you could have the case where you've got a number c, where the second derivative is 0 or undefined. And this is for the second derivative. Say that it changes plus, 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 minus, 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 minus. This might be a case where to the left of C you're a concave up, to the right of C you're a concave down. Okay. Or this time maybe you're going minus, 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 plus, 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 plus. So the second derivative changes sign at C from negative to positive. Instead, though, the function might always be decreasing. Oops. My C should have been more right here. Okay. Another possible case. So this time you could have plus, 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 minus, 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 minus. So the second derivative changes from positive to negative at a number c, but instead you are decreasing the whole time. Okay. And then the last possibility is that you are decreasing. Oh, I already drew that picture. Increasing, decreasing, and decreasing, and something that's increasing concave down. Yeah, this picture should have maybe been something like this. There we go. I like that better than the last picture on here. So there's some different possibilities, right? You can be increasing and change from concave up to concave down. You can be decreasing and change from concave up to concave down. Or the vice versa for the other case. You can be decreasing and change from concave down to concave up, or you can be increasing and change from concave down to concave up. So there's several different possibilities for what can happen.
Right.
Yeah.
Just how do you draw the difference between the? Oh, never mind.
See it?
Yeah.
Okay. All right. So just keep in mind there's several different possibilities, right? You can be increasing or decreasing and change from concave up to concave down, or increasing and decreasing and change from concave down to concave up. So we're going to do an example looking for inflection points. So find the inflection points of f of x equals x cubed minus 9x squared plus 24x minus 10. So again, this is another cubic polynomial. I've added 3 extra terms though this time. And we're just looking for the inflection points. So we want to know the points on the graph where concavity changes. And generally, we'll find the x and y coordinates of those inflection points. Okay, so what are the coordinates of the inflection points? Okay, I guess I did skip a number. The inflection points can only occur at partition numbers. So your inflection points only happen where the second derivative is 0 or undefined. Okay. let me wait a minute, just make sure everybody has these cases. I guess they're kind of broken down on your handout already. Is it okay if I erase these top two? Okay. All right, so if I want to find inflection points, that means I'm really using which derivative? Okay, you use the second, right? The first derivative is for increasing and decreasing and where the local max and mins are. The second derivative is for concavity and where the inflection points are. Okay. So we're going to need a couple derivatives, so we can start by finding the first derivative, which is 3x squared minus 18x plus 24. And then the second derivative then would be, what is it, 6x minus 18. And we could do the whole analysis, right? I could use that first derivative to find local max and mins in intervals of increase and decrease. And the second derivative now, I can use that to figure out where the concavity is, or what the concavity is, and then also where the inflection points are. So the second derivative equals 0 or is undefined. Well, it's never undefined, so we only care about where it's equal to 0. And then can anybody just look and see what it is? Yeah, right? What do I have to multiply by 6 to get 18 and make a 0? So the partition number, in fact, I'll write the only partition number is x equals 3. So that is possibly a place where the concavity is going to change. So you can make your sign chart now for the second derivative. I'll put positive 3 on here. And then you can think about plugging test values. I've now split this up into 2 intervals. Okay, so let's see. If I take things to the left of 3, so what's an easy value?
0.
You can use 0. If you plug 0 into the second derivative, you get minus 18. So the second derivative is negative to the left of 3. And if you plug anything bigger than 3 into the derivative, you're going to get, well, 6 times 4, for instance, is 24 minus 18. That'll give you positives. Okay. So your concave down to the left of 3, and the graph is concave up to the right of 3. And then, just so we have some practice, I'll write this. The graph of f is concave down on the interval from minus infinity to 3. Okay. I should have probably written the domain of the original function down too. You want to know where you're working, right? So make sure you're always thinking about what domains are. I should have written the domain of the original function was all real numbers. So on that domain from minus infinity to 3, you're concave down, and the graph of f is concave up on the interval from positive 3 to infinity. And therefore, where's my inflection point going to occur? So 3 is a number in the domain where the concavity changes sign. So the inflection point is 3 comma f of 3. So that's the point on the graph where that concavity will change. And then I just need to know what f of 3 is. I don't know if my arithmetic's going to be very good today. I'm kind of off. 3 cubed is 27 minus 81. Yeah, I'll just do it in the calculator. Okay. Anybody get a value for f of 3? I want to make sure that we're on the same page. Did you get something yet?
No, I'm plugging in right now.
Okay. You get 62?
Yeah, I did too.
That means I probably didn't do order of operations correctly.
No, I forgot to square the second term.
I'm actually getting something different.
Yeah, I messed up.
Reese, what'd you get? You got 8? Yeah, that's what I got too.
I initially got 8, but I wasn't sure.
Okay. So it does end up being 8 when you do 3 cubed minus 9 times 3 squared plus 24 times 3 minus 10. So remember, once you know where the x-coordinate of the inflection point is, you're always plugging that into the original function to get the y-coordinate of the inflection point. Just like when I know I have a local max or min at a particular value, I plug it into the original function to find the local max or local min. Okay, so at the point 3, 8, that's where you change from concave down to concave up. So only one inflection point for that graph. How much time do you have? 10 minutes, 15 minutes? Okay. So now what we're going to do is we're going to, example 3, I'm going to take not the graph of a function f, we're going to look at the graph of its derivative, and I'm going to use just that to sketch a graph of the original function. Okay, so anybody have any questions on this? Okay, for inflection points, find a second derivative. Find your partition numbers where it's 0 or undefined. Once you find those partition numbers, you put them on a number line, pick test values, and then note the sign on the second derivative. And then if that number is in the domain and the concavity changes, it leads to an inflection point. Okay. All right. All right, so everybody okay with that one? All right. So for example 3, just give me a minute here to draw a sketch of this graph. And again, this is the graph of f prime of x. So let's see if I go 1, 2, 3, 4, 5. It looks like I got a y-intercept at just below positive 2. I'm going to use black for this actually. And then I can go, I guess we're just going 5 tick marks in every direction. Then just 1, 2 down. So you're 0 at -1. You're also 0 at positive 2. You've got a local max at positive 1 just above positive 3. Okay. I think that looks close enough, right? Probably don't need this going all the way down here. There we go. Okay, so that's not the graph of f, that's a graph of the derivative. So what I'm going to do now is I'm going to make a little table. I'm going to note down all the important information. Okay, so we're going to find intervals of increase and decrease. Okay, we're going to find the intervals of concavity. Now, there's actually more than one sketch that'll work. So for any derivative, there's actually infinitely many functions that would have this graph for its derivative, it turns out. Okay? I don't make everyone responsible for that fact, but there's lots of different graphs I can draw here that would work. Okay, so let's make a table and organize a bunch of information. So let's see. So I've got f prime of x is greater than 0 on what interval? F prime of x is less than 0 on what interval? We'll figure out where the second derivative is greater than 0 and where the second derivative is less than 0. So we've got to find all these intervals. I think it's easy to deal with f prime first. Okay, so what do we know? Well, since this is the graph of the derivative, I just want to know which intervals the derivative is positive. So to me it looks like you're above the x-axis from minus infinity to negative 1. And then from minus 1 to positive 2. Okay. Right, and then at minus 1, the derivative is exactly 0. And as a matter of fact, if it makes it more helpful, we can kind of convert this into a sign chart for f prime. Okay, so essentially the critical number is going to be negative 1, right? Because that's where the derivative is 0. And we're going, let's see, well, positive 1 and 2, my bad. So you have two places where the derivative is 0. Here it's going to be plus, 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 plus. And then at negative 1, that's where the derivative is 0, but then the function stays above the x-axis, right? The derivative is still positive. But then once you get to negative 2, the derivative becomes negative because now it's below the x-axis. Okay, so everybody okay there? Again, that's the graph of the derivative. It's positive whenever you're above the x-axis. It's negative where you're below. Okay, so f prime of x is less than 0 on the interval from 2 to infinity. And then the second derivative, remember, wherever the first derivative is increasing, the second derivative will be positive. Wherever the second derivative, well, wherever the derivative is decreasing, the second derivative will be negative. So now we got to think about tangent lines on our graph of our derivative. So let's start from left to right. So if I start up here, right, the tangent line on the derivative is really negative, but as we get closer and closer to this point right here, the slopes of the tangent lines seem to be doing what? Increasing, right? Okay. Although, wait a minute, I shouldn't be looking at f. I made a mistake here. This is, again, and this is an easy one to make, I was treating f prime as if it was the original function. Okay. Go back to your concavity definition. You're concave up wherever the first derivative is increasing. You're concave down wherever the first derivative is decreasing. So I made a mistake there, so my bad. So here, the derivative is decreasing until you get to minus 1. So that tells me that the second derivative is less than 0 on minus infinity to minus 1. And is there another place where the derivative is decreasing?
From 1 to infinity.
Yeah, there we go. So the derivative is decreasing from 1 to infinity. So wherever the graph of the derivative is going down, that's where the second derivative is negative. And then how many places are there where the derivative is actually increasing or the graph is going upward?
Negative 1.
Yeah, there's this one place from negative 1 to 2, negative 1 to 1, right? That's where the first derivative is increasing, so I should actually be going minus 1 to 1. And if it's helpful, I'll convert that information into a number line. So let's see, there seems to be two possible inflection points. Right, the first one is right here. Again, don't treat this like it's the original function. Right, I don't care what the inflection points of the derivative are. I'm just using the graph of the derivative to find possible inflection points. So what I should be saying is the first derivative changes from decreasing to increasing at -1. So that's where you'd have an inflection point on the original graph of f. And then where's the other place? Well, the derivative changes from, I guess up here, the derivative changes from increasing to decreasing at +1, and that's it. Okay. So let's see, the first derivative is positive only between, the second derivative is positive between -1 and 1, and the derivative was decreasing, you're going to get minus signs on these outside intervals.
So would you have a concavity change, like, at 0, or is that only...
So the only concavity changes are going to be at -1 and +1.
Okay.
Because the first derivative is changing from decreasing to increasing at -1. And then, again, you're changing from increasing to decreasing at this point.
Okay.
The first derivative is increasing till there, and then the first derivative starts decreasing.
So whether it's like sloping up or whether it's starting to curve towards like the maximum, that doesn't mean it's changing the sign of the second derivative.
No.
Okay.
It's just where the first derivative changes from increasing to decreasing or vice versa.
Okay.
So where it changes from going up to going down. Okay. And then now we should be able to sketch a graph. And we can make up whatever we want. Okay, so
Are the mins and maxes of the original equation when x equals 0 on the derivative? So where?
So the only place where the derivative changed sign was at 2. Because the derivative went from being above the x-axis to below.
That's where.
Yep. And there,
right.
we changed from positive derivative to a negative derivative, meaning at 2 there's going to be a local maximum.
Yeah.
And there's actually 2 inflection points. You have to have an inflection point at -1 and at +1. So the left half of the graph is going to be the easiest to draw, because where the first derivative is positive, our original function is increasing, but we also know it's supposed to be concave down. So I'll just make something up. Let me maybe use blue here. So maybe our function is increasing until I get right here at -1. Okay. And that agrees with both sign charts. Because the derivative's positive, so the function's increasing, but the second derivative's negative, which means it's concave down. Okay. And then now this is where it gets a little tricky too. So you're going to have, at +2, we're going to change from increasing to decreasing, but also at 1, the second derivative changes from positive to negative. Okay, so let's see if we can do this. So it's going to be positive here. Maybe I should have written this. Concave down, concave up, concave down. This was increasing, increasing, decreasing. So now we have to be at first, well, certainly from -1 to 1, we're concave up and increasing. So maybe from -1 to 1, we're concave up but increasing. Okay, so from -1 to +1, we're increasing and concave up. Okay. But then it's going to change to concave down, but it's still going to be increasing until we get to 2. So we'll change to concave down. Here's 2. That's where my local max is going to be.
And the height you just estimated?
Yep, I just made it up.
Okay.
Yeah, because like I said,
Oh no, we don't have the
there's infinitely many functions that can work. In fact, once I've drawn a function, it can be shifted up or down anywhere I want, and it would be a function that would work. And then what happens at 2, so we're still going to be concave down, but now the function is going to be decreasing. So it's going to look something like this. So it's tricky. It's tough to keep track at first, and like I said, you went from we just had the graph of the derivative. Where the derivative is positive, well, that's just where it was above the x-axis. We wrote down the intervals. Where the derivative was negative, that's where the graph was below the x-axis. And then the second derivative being positive is wherever the derivative is going down, decreasing, or sorry, up for positive. So wherever the first derivative was rising, which was only between -1 to 1, and then the second derivative being less than 0 is anywhere where the derivative was going downward. So negative infinity to -1, and then 1 to infinity. Okay, and then I converted that information to 2 sign charts, and then you can draw any graph you want that just agrees with the sign charts. So your graph, this can be shifted up or down anywhere you want, and it would still satisfy the sign charts. Okay, and that's all I got for today. I'll see everybody tomorrow.